All right, so today we're going to talk about the truth values of complex statements, and we're going to introduce truth tables. Essentially, truth tables are a mechanical method for determining all possible truth values of a statement. What you do is you set up all the letters of a statement on the left side of the truth table. You set up alternating trues and falses for the innermost, and then you double it for each subsequent letter. So if there were a third letter, we would do 4 falses and then 4 trues. If there were a fourth letter, we would do 8 falses and then 8 trues, and so forth. So in other words, truth tables get exponentially more complex with each additional letter. But we're going to start easy. We're going to start with 2 letters, which are going to require 4 rows. The zeros are false. The ones are true. This is basically binary. So here is the truth table for, we're going to run through the truth tables for each of the basic functions. The AND truth table, essentially the AND is false whenever either or both sides are false. The only circumstance in which AND is true is when both halves are true. The OR truth table is the opposite. OR is true if either side or both sides are true. So OR is true in 3 of the 4 situations. If the left side is true, it's true. If the right side is true, it's true. If both sides are true, it's true. The only circumstance in which the OR is false is where both halves are false. So the and or sort of reverse of each other. The and is false in 3 of the 4 circumstances, only true when both halves are true. The or is true in 3 of the 4 circumstances, it's only false if both halves are false. I think those 2 are fairly straightforward and intuitive. Now, this is the one that I judge to be the most counterintuitive of the basic operators, the conditional, the arrow. So the arrow claims if P then Q. It is true in 3 of the 4 circumstances. It is only false in the circumstance where the left side is true, but the right side is false. And I think the easiest way to think of this is think of this as a promise. And think of a promise as a conditional statement. If you fulfill a certain condition, someone will do something for you. If you get a 93 average in this class, you will get an A. Promise from me to you. Under what circumstances is that claim a lie? That claim is only a lie under one circumstance. If you get the required average, 93 or above, and yet for some magical reason you do not get an A, that would be false. That would make this conditional statement false. Under every other circumstance, we assume the promise has been fulfilled, or at least is not false. So if you, for some reason, don't get the A, or rather, if you don't get the 93 average, then whatever you get in the class, the claim has been true. And if you get the 93 or above and also get an A, then the promise has been kept. So the only circumstance in which there's been a broken promise is if you fulfill the conditions of the promise and it is not fulfilled. Again, if then, true on 3 of the 4 situations, it is only false when the left side is true but the right side is false. All right, next is the if and only if truth table. If and only if, as I've said before, is basically the claim that the 2 sides of the triple bar statement will match. It is true when both sides are false, and it is also true when both sides are true. But if only one side is true and the other is false, then the statement in its entirety is false. So if the sides don't match, then the value of the triple bar is false. And here's a super easy one. This is the negation truth table. When P is false, if you negate P, it switches the value of P to true. If P is true and you negate the true, it becomes false. All right, now I have repeatedly attempted to get IT to fix this, and for some reason they have not. So we're just going to have to talk these through together. But it's important that you get these down cold, because shortly we will be doing problems where you have to calculate the values of 16 and 32 statements in one problem. So you need to get these right 100% of the time, or 98, 99% of the time. This needs to be like basic arithmetic, basic English language. If you don't have this down cold, get some tutoring, get help, ask questions, because I don't want to leave anybody behind. But we need this down cold. All right. So this is an OR statement. It is false on the left and true on the right. What's the value of what's the statement value then? The statement value is
true.
True. Why?
This OR requires one of the values to be true.
Good. When either side of the OR is true, the OR statement is true. Very good. All right. This is an AND statement, and it has false on both sides. What is the value of the AND statement? Okay. Why? Good. So yes, this is false. All right, this is a conditional statement. Looks strangely like an owl to me. But it is false on both sides. What is the value of the arrow statement when it is false on both sides? It's true. Why?
Because that only counts as false when the first part of it is true and the second half isn't.
Good. Yes, so this is one some people find counterintuitive, but anytime the left side of a conditional is false, the arrow conditional statement is true. So this, despite having 2 falses, this statement is true. Negated 0. What is the value of negated 0?
True.
Yes. 0 is false. Negation switches it to true. Shocking. 0 triple bar 1. What is the value of 0 triple bar 1? Yes, sir. It is false. Why? Good. The triple bar is the claim that the two sides should match. The two sides do not match. Therefore, it is false. Very good. 1 asterisk 0. What is the value of 1 asterisk 0? Yes, ma'am. False. Why? Good. Yes, that is correct. 1 arrow 1. What is the value of 1 arrow 1?
True.
True. Good. Why?
If then statements are only false, if the beginning part of the if is true and the then is false.
Good. Another way of thinking about it is anytime the right side is true, the arrow is true, or anytime the left side is false, the arrow is true. There are multiple ways to think of it, but good. 1 triple bar 1. The value of 1 triple bar 1 is true. All right. I think they've got it. Let me see. Are there any of these that I feel like we should talk about? All right, this one. This is the only one where the arrow statement is false because it's true on the left. The conditions of the statement have been fulfilled, but it is false on the right. The promised consequence has not occurred. So the arrow statement is false. All right. Let's kick it up a notch. That was easy stuff. Let's make life harder. So far we've been nice and we've only been doing statements with 2 letters at a time. But let's make it more complicated. Let's make it 3 letters. And let's throw in some negations. So how do we determine the value of a 3-letter complex statement like if P, then Q, if and only if, not R? All right, so let's suppose the values we want to figure it out for are P is true, Q is false, and R is false. Excuse me, I need a wipe. All right, so if P, then Q, if and only if, not R. If P, then Q, if and only if, not R. Step 1, we need to plug in the truth values in place of the letters. So we've already told you P is true, Q is false, and that R is false. We keep everything else the same, all of the negations, all of the operators, all of the parentheses. So step 1, plug in the truth values in place of the letters. And that's what this is right here. Then it gets more complicated. Then we assess the truth value of the operations, starting with the most internal parenthetical operation. This should feel familiar. This is how it works in any high school level or above math. When we have multiple nested parentheses, we always start with the most internal one. So if the statement, if true, then false, that is the one circumstance where the arrow statement is false because it's true on the left and false on the right. Then we carry that down, we remove this parentheses statement entirely because we've got the solution for that. And then we continue. Now, when you have a negation inside of the parentheses, you have to apply the power of the negation before you do the operator. So since we have a negation inside the parentheses, we need to apply it before we can figure out the value of the operator. So the negated 0 switches to 1, so the negated false switches to true. So then our final step, we have 0 triple bar 1, and that statement is false because these sides don't match. All right, how's that sound? Intuitive enough? Now we have to distinguish between the situation where you have a negation outside the parenthesis and a negation inside the parenthesis. You apply the negation inside the parenthesis before you can do the operator. But if there was a negation outside the parenthesis, you would not apply it until the very end. You would keep bringing it down until here, and then you would apply it dead last. All right, let's do some problems. Let's do some problems with A being true, B being true, X being false, and Y being false. And you know what? Let's have some fun. Let's actually have like people put some stuff on the board. You've heard enough of me doing your logic for you. Let's get some victims, some volunteers, as it were. And let's put some things on the board. Who'll do number 1 for us? All right, come on down. Do number 1 for us. Who'll do number 2 for us? Let's do 3 at a time. Who'll do number 2 for us? Yes, sir, you do number 2, and who'll do number 3? These aren't that difficult. Yes, sir, let's get you. All right, so here, let's give you one. Let me erase this mess. All right, thank you. Thank you. All right, so go put number 1 up in the left corner, put number 2 in the middle, put number 3 in the right. Go for it. First one is, there you go. Negated A and X. Here, I've got the problem for you. All right, very good. Let's look at number 3 first. Number 3 claims it is not the case of both not A and not X. First, we plug in the values. A is always true, X is always false. Then within the parenthesis, we need to apply the negations first. False switches to true, true switches to false. Then we look at the AND operator. Since 1/2 of the AND is false, the entirety of the AND is false. Then finally, we apply the negation to the false, which switches it to true. Very good. Let's see what else we got. Number 1 is not the case of both A and X. A is true, X is false. We look at the and is false on one side, therefore the and is false. Then the last thing we do is apply the negation to the false, and it switches to true. Very good. Here we have not A and not X. We plug in true for A, we plug in false for X. Then we apply the negations. The true switches to false, the false switches to true. Then we look at that, and half of it is false, so the and is false. Very good. All right, let's get some volunteers to look at 4, 5, and 6. Who'll do 4 for us? Please, why not do 4? We'll do 5 for us. Thank you. So, let's do that. Let's do number 6. Who's going to do number 6 for us? Yes, ma'am. All right, let's look at number 5. Number 5 claims not X if and only if Y. We plug in the zeros for both halves. We apply the negation to the one half that's negated. We get true on the left, false on the right. The sides do not match, therefore the triple bar is false. Very good. Number 4, if A then X. We plug in true for A, we plug in false for X. That is the one of the 4 combinations that makes the arrow false. Therefore, that is correct, the arrow is false. Number 6 says if not B, then A. We plug in true on both sides. We apply the false on the left side, which makes the true false. Rather, we apply the negation, that is. And that is a combination that makes the arrow statement true. All right, how's it going? How's this seem? All right, what would be helpful? All right, I think you've got the 2 position ones down. Let's start with 8. Can I get somebody to do 8? Actually, hold on a second. Let me erase the board. Then I'll get somebody to do 8. All right, can I get a volunteer to do 8 for us? Want to? All right. Be brave. Who will do 9 for us? Yes, sir. Please come on down and do 9. We will allow double dipping at this point. Who will do 10 for us? Can't succeed if you don't try. All right, do 10 for us. Ready for that. 8 is B and parentheses X or A. Close parentheses twice. 10 is open parentheses, not A, or negation, new parentheses, X arrow Y. Y, and then close parentheses twice. Very good. All right, let's look at 9. 9 claims either it is not the case of both X and A, or not B. We plug in the values of false for X and true for A and B. We start with the innermost parenthesis, the and, which is false because it's false on one of the halves. Then IC's also applied that negation, which is perfectly acceptable. Then we apply this negation to that side, which is false, switches to true. Then we get the final value. The final value is true because half of the or statement is true. Very good. Let's look at 8. B and either X or A. Plug in the trues and the false. B's and A's are trues. X's are false. We start with the innermost parenthesis. It's an or that is true because half of it is true. We then have an and statement that's true on both sides. The entirety of the statement is true. Here we have either not A or it is not the case of if X then Y. We plug in the values true for A, false for X and Y. We do the innermost parentheses. It's an arrow statement that is true because the left half is false. We then have a negated true on each side. We apply the negations to each side of the or, and if it's false on both sides, your statement is false. All right, guys, you all are doing just fine. Use guys. I try to recover my board members. You all went too much later. Questions? How's it going? All right, now here's my fear. My fear is the 10 people who've gone up to the board have it down cold, and the people who haven't approached the board are not doing as well. So let me talk to y'all who have not y'all. Let me talk to y'all who've not been up to the board. How's it going? How are we doing with this? Give me something. Give me a thumbs up if you're good. Give me, just be honest with me. Give me something wavering if there's still some struggles. All right. Let's do this. I want to ask the people. I want to ask for one of the hardest things for somebody to do. Somebody who's struggling. I want you to come up to the board and work one of these problems with me. Because that's how we're going to learn. We okay with that? All right, well, let's see if I can get somebody to actually volunteer. Who's going to do 11 for me? I mean, I'm not going to make it. Yes, sir. Come on down, do 11 for us.
So one of the problems is I forgot my book.
Guess who has a book? Sanitize well. Thanks. All right, so problem 11 is double open parenthesis, A and not X, close parenthesis, arrow, not B, close parenthesis. All right, what do you do first?
Turn them into ones and zeros.
Right, plug in the ones for A's and the zeros for X's. The ones for A's and B's, that is, and the zeros for X's. Good. And what do you do next?
Do the knots.
Good, so you go to the inner parenthesis, and within the inner parenthesis, you apply the not. So good. And what do we do next?
Let's see if it's true or false.
You go to the inner parenthesis, and you determine the truth or falsity of just the operator in the inner parenthesis.
This is true, right?
That is correct. And is true when it's true on both sides. Oh, wait. So you just pull a 1 down. So then you have 1 arrow 0. Good. And then you figure out the value of the 1 arrow 0.
This is false.
And that is false. That's correct. And voila! I think he's got it. Excellent. Let's see. Let me skip ahead to the hardest problem of exercise 6.3a, and that's number 15. Because those of you who are willing to do these, you've mastered everything to this point. So number 15 is this. Negation outside of 2 parentheses, A, arrow B, arrow, new parentheses, B, arrow, Y, end double parentheses. Step 1, plug in the numerical values. Step 2, go to the innermost parenthesis and solve the innermost parenthesis problem. All right, so this is an arrow that's true on both sides. That makes it true. We'll go to this inner parenthesis as well. That's an arrow that is true on one side and false on the other, which makes it false. We bring down this arrow because we've not solved that arrow. We bring down the negation because we've not applied the negation because it's outside all the parentheses. We then solve this problem within the parentheses, which is false. We then apply that negation, which makes it true. Everyone see how I got that? Good. Well, that's the hardest one in this this section. So we are graduating from this section, and now we can make things harder. Good job. Okay, next section, 6.4. 6.4 does this. 6.4 teaches us how to use truth tables to attempt to solve a compound statement when we don't know the value of one of the letters. And what we will see is sometimes the truth table will help us establish what the value is of the statement, even when we don't know the value of one of the letters, and other times it will not. So here, on these two truth tables, P is always true, but U stands for unknown. And because it's unknown, we need to calculate the value of the statement for both possible values. And it turns out when we have the statement P, where P is true, or U, where U is unknown, we still can figure out and prove the value of the OR. Because no matter what the unknown value is, the value of the OR is going to be true. So we run it the first time with the unknown value is false, and the wedge statement is true because the left side is true. And then we run it again with the U as true, and the value of the OR statement is true because both sides of the OR are true. So therefore, this truth table has proven that the value of the OR is true on P or unknown when P is true. In contrast, if it were an AND statement where P is true, but the unknown we don't know, on the first set of values where the unknown value is false, the AND is false. But then when we switch it and make the unknown value true, the AND is true. Therefore, we put a question mark there because the value of the AND statement is unknown without more information, because it changes when the value of the unknown statement changes. All right, so that's a quick primer. The two-step truth table shows us that sometimes we can calculate the value of a statement without knowing both values, and sometimes we can't. Shocking. All right, so here, let me set a few of these up. And I think this is where, not this particular one necessarily, but I think this set of problems is where it starts to get a little harder. Because I think we've been doing quite well so far. All right, so unknown and false. All right, so here is the values that we're going to use. False F's stand for falses, which are always 0. T's stand for true, which are always 1s. And U stand for unknown, which we have to plug in both the true and the false to determine their value. So let's say we have the statement, unknown and false. We put zeros for both places for false, because false is always false. And we put a 1 and a 0 in for the unknown, because sometimes it's true and sometimes it's false. So on the first case, we have an AND with a false on one side. Therefore, it is false. And then in the second case, where the unknown is false rather than true, then we have an AND that is false on both sides. And therefore, the value of that statement is false. Therefore, the value of the equation is always false, no matter what the value of U is. And that's the point that we're trying to get to. All right, let's do another one. What if we have unknown? If unknown, then not true. All right. On the first set of values where the unknown is false, first we have to apply the negation to the true. We then see that both sides of the arrow are false, which makes the statement true. Then let's look at the second set of values where the unknown is true. We have to apply that negation to the true. Then we need to figure out the value of that statement, which makes it false. So when the unknown is false, the statement is true. But when the unknown is true, the statement is false. So the value is unknown or question mark. Everyone see why? It's because the value of the statement changes when the value of the unknown changes. All right, let's do a harder one. And by the way, there will be problems like this on exam 3. So again, I want you to have this down for the exam. Let's get one with 3 digits. All right, let's do number 8, which is B and, oh, that's 6.3. Let's do, oh, all right, how about that? All right, none of those are particularly difficult to make. All right, let's do that. If unknown, then not false. Again, false, the F is always false. The unknown will sometimes be true and sometimes be false. On the first set of values, we put false on both sides. Then we have to apply the negation to the 1/2. That makes the left side false, but the right side true. Then we have to solve the arrow, which is true. Then we have to plug in the unknown as true instead of false for the second set. Again, we apply the negation first. And here again, the arrow is true because both halves are true. And the value of the statement is 1, no matter what the value of the is. Questions on how to solve problems with unknown values. All right. Well, we will do 6.5 and 6.6. We'll do, actually, we'll do 6.5 for next time. Thank you very much. Hang in there. And we're going to put more things on the board together. So don't be shy. Come prepared, ready to put things on the board. Thank you very much. How's it going? Excellent. Glad to hear it.
Just wanted to.
Okay, you're welcome. How is, are you in that Phil language class with tweets?
No, I'm not.
For some reason I thought you were in that. Are you in another philosophy class right now?
Yeah, the senior seminar right now.
Yeah, how's that going for you?
Good. Just waiting to get comments back from professors on my second draft.
What's your thesis?
Trying to remember exactly the way I formatted it, but basically a theology of liberation rooted in contemplative action helps the church correct the harms it's caused by allying itself with the coal industry.
With the coal industry, that's right. So what does a theology, a coal-friendly theology look like?
So this isn't, it's supposed to be anti-coal.
Well, yes, I know, but you said the harms that it's caused, so I took that to mean that in the past it's been sort of pro-coal.
So some of the frameworks that have, so a lot of my cases specifically revolve around the Diocese of Wheeling, Charleston, in West Virginia.
That makes sense. That's coal country.
Yeah, with Bishop Michael J. Bransfield, and part of the way he justified the coal industry itself and what it does in the region is basically promoting the dignity of human labor offered by providing jobs in the region.
Sure. Well, that's